Welcome to the second presentation in Unit 9 entitled Mangia, bene, vivi, felice. And I'm sure I butchered that. It means eat well, live happy, and it's an Italian proverb. So, the goals for this presentation are that you be able to dilute a solution to an appropriate molarity, including using the process we know as a serial dilution. We also should be able to relate the change in colligative properties to the intermolecular forces, colligative properties being things like boiling point and freezing point. And you should be able to conceptually describe the factors that affect the solubility of a solute. So if I have sugar and I want to get as much sugar as possible into water, what can I do to the water to make sure that I can add as much sugar as possible? So, what we already know. We already know that solutions can vary depending on the concentration of a solute in solution. So we know we can have things that are very concentrated, and we know that we can have things that are very dilute, where you just have a few solute particles. We also know that the higher the concentration is, the more solute or solvent there, or the more solute per solvent there is. We know that polar solutes require polar solvents, and we know that light can be absorbed or reflected by substances. So, what we learned in the lab, we learned that adding salt to a solution can affect the boiling point of a solvent. We saw that as we added more salt, we saw the boiling point temperature actually increase. Okay, like we see whenever you add salt water or whenever you add salt to pasta water. The more salt added, the greater the change in boiling point. So we ended up with having a much higher boiling point the more salt that we added. Okay, so the first thing we need to look at is diluting a solution. This formula is called the dilution formula, and it's how you can figure out or how you can calculate a new molarity or how much you need to dilute a solution by. Now, this formula works by the process of this. The number of moles that you have equals the number of moles. So, for example, if I have a very concentrated solution, okay, if I were to take and dilute that solution, I would still have the same number of particles. They would just be more spread out. So this is a more dilute version, and this is the more concentrated version, but the number of moles are the same. That's the basis behind the dilution equation. So you have the molarity of the first solution, the volume of the first solution, the molarity of the second solution, and the volume of the second solution. When we're talking about dilutions, we are just going to use molarity. We're not going to use molality or parts per million or parts per billion. So, there is also a process called a serial dilution. The serial dilution is very useful because large dilutions tend to be inaccurate and wasteful. So for example, if I need to make a solution that is like 1.0 times 10 to the minus fifth molar of sodium chloride, that is a very difficult solution to make because you would have to measure out 55 grams or 58.5 grams and then divide it by like a billion, or not a billion, a million liters. So it ends up being very difficult for you to be able to do and wasteful in terms of the amount of water you use. So instead, what we do is we do a serial dilution, which is a process of repeated dilutions. So what you would do is you would create a 1 molar sodium chloride solution, and that would use 1 liter of water. But then what you can do is you can take a small sample of this and then dilute it. And you could dilute it to 0.1 molar. And take a small sample of this and dilute it to 0.01 molar. And take a small sample of this and dilute it to 0.001 molar, and so on. The process of a serial dilution uses a lot less solvent, a lot less material, and is less wasteful, and also produces greater accuracy. The likelihood that you are going to be able to accurately measure 58.5 grams is pretty reasonable, but that you are going to accurately measure a million liters is not. So because of that, the serial dilution process has its advantages whenever you're trying to make very small or very dilute solutions. So it says, which of the following represents the diluted solution? It is this one because they have the same volume. Okay, if they have the same volume, remember molarity is equal to the number of moles divided by volume. Since the volume is a constant, we can take that out and we can just look at the number of moles. Now, if these beakers were different sizes, that's not something we could do. We would have to look at the ratio. But because they're the same size, the only thing that matters is the number of particles. Next, it says a student needs to dilute a stock solution. Stock solution means it is guaranteed by the supply company that this is the true concentration. Okay, a lot of times when we make solutions in the lab, we're not quite sure what they are. These are tested and proven to be those values. So it says we need to take a dilute solution of 15.8 molar HCl to zero point 0.1. It says the student estimates that she needs 250 mils, but always makes an additional 20% for insurance. Okay, that's a good process to have. Like if you think you need 250 mils, you don't want to have to stop in the middle of it in order to make more solution. So what you'll do here is it says, okay, what is the minimum amount of stock solution the student can use to get the solution she needs? So let's look at it. The first thing is I know the first molarity. The first molarity is 15.8 molar. The volume of the stock concentration is what I need to know. The molarity of the second solution, the one that I want, is 0.1 molar, and the volume that I want is 300 mils. That's what you get whenever you have 250 mils and you add a 20% for insurance. You multiply that out, you get roughly 300 mils. So now I can plug it into the equation that I know M1V1 equals M2V2. 15.8 V1 is equal to 0.1 times 300. So you would have 30 is equal to 15.8 V1. Whenever you divide this out, you end up with a volume of about 18.99 mils. So whenever you're doing a dilution like this, although the significant figure said that we should really round this to be 20 mils, okay, whenever you round it to 20 mils, that's going to throw off the concentration quite a bit. So whenever you do these dilution calculations, you would try and measure this to the best of your abilities, even though the significant figures say that this is not a big deal. That's also a reason why the serial dilution is a better process. In this one it says, a student needs to generate 5 mils of 2.4 times 10 to the minus 6 molar solution. So once again, this is very, very, very dilute. For an experiment to observe how changing the pH levels can influence cellular behavior, the student has 2 molar stock HCl concentration. So this is something on the order of about 1,000,000 times the concentration that we need. So we don't want to use this solution and do a straight dilution. Okay, if we were to do that, it wouldn't make any sense it wouldn't work that way. You wouldn't be able to get a reasonable solution. So if you do the math just to kind of check it, if you did 2 times volume 1 equals 2.4 times 10 to the minus 6 V2, excuse me, I need 5 mils of that. Okay, then you were to multiply this out, you would end up getting a volume that you would need to measure of the original solution of 0.005 zeros. Oh, I wrote one too many. 5 zeros, and then a 6 mils, which is too small for you to be able to actually measure. So because of that, we know that we would do a serial dilution. Now, serial dilutions are generally done in a 10 to 1 dilution. So in other words, what you would do is you would take 2, and 2 would go to 0.2, and then would go to 0.02, and then would go to 0.002, and so on. But in order to do that, the first thing we need to get it is to the 2.4 that we need to be. So the first thing I'm going to do is I'm going to kind of erase this, and I'm going to say that instead of trying to just go to 0.2, I'm going to go to 2.4. Okay, so here's the value that we're going to do. We're going to go from 2 to 0.24. That is very, very close to a 10 to 1. Then we're going to go from that to 0.024, then to 0.0024, and then to 0.00024, and so on. So we're going to set up the process of a serial dilution. So the first step is really the only one that's any different. We'll do the first two, and then the rest of them are going to be the same until you get to 2.4 times 10 to the minus 6th. So once you do this, you would say, okay, I need to convert from 2 molar to 0.24 molar. So I would say, all right, 2 molar times volume 1 equals, and then what we're going to do is we're going to set the value here to say I want to make 10 mils. Okay, if I make 10 mils, that would give me enough to be able to do the next dilution and have a little bit over if I made a mistake. So once you do this, you would be able to calculate the volume that you would need there. and then whenever you calculate the volume, it's 0.24 times 10, which is 2.4, divided by 2, which means you would need 1.2 mils of HCl, and then you would need a total volume of 10. Okay, so if you were to do this, you would add 1.2 mils of HCl, and you would add 8.8 mils of water. When you do that, you are now at 0.24. So now to go from 0.24 to 0.024, we're going to change the color just so it's a little easier to see. You have 0.24, and you don't want to use the entire 10 mil sample. You notice how we made 10 mils right here? You don't want to use that entire sample. Instead, we're going to take 1 mil out, a smaller volume, and then on the other side, we're going to produce 0.024, and we can figure out what we need to dilute it to. Okay, if you were to take 0.24 times 1 and divide it by 0.024, volume 2 ends up being 10. So here's where you get that whole idea of the 10 to 1 dilution. So you would add 1 mil of the 0.24 solution to 9 mils of water. And that's the process of a serial dilution. So you take 1 mil of this, 9 mils of this, and the total volume ends up being the 10 to 1 dilution. Next, we need to talk a little bit about colligative properties. Colligative properties are physical changes that result from adding a solute to a solvent. So colligative properties depend on the ratio of solute to solvent, or how concentrated a solution is. When you add more of one thing, it's going to change a particular property that makes it a colligative property. One colligative property that we need to look at is freezing point. And freezing point is you have a partially positive hydrogen atom and you have a partially positive negative or partially negative oxygen atom. There's an attraction between these water molecules because of the fact that they have this polar bond. Okay, so you have an intermolecular attraction. Remember we talked about earlier in the year, we said opposites attract. So when you have another partial positive right here, there's an attraction between different water molecules. Okay. Now, when you add solute to it, okay, what you're doing is you're adding an ionic compound. The ionic compound consists of cations and anions, which have a full positive and a full negative charge. It's not a partial positive. It's not a fraction. It's not like 1/3 of a positive charge. That's not what it is anymore. Now it's considered to be a full positive charge and a full negative charge. So what happens is the water molecules are very, very, very attracted to these cations and anions. Now it's really important that you realize that this is not a bond. It is not H2OCl. That's not what it is. What we're saying is that the oxygens, that these hydrogens right here are attracted to the chlorines. Okay, that's why we generally draw it as a dashed line. It indicates what we call an intermolecular force. It's just saying that they're attracted to, but they're not stuck to it. The freezing point depression. Your engine does not freeze when it's icy outside, and the reason why is you add something called antifreeze. The antifreeze works the same way. You add a solute and it changes the freezing point of the solvent. So whenever you were to just take sodium chloride and add it to water, as you do this, you can see the temperature start to decrease very much. Now, if you were to use something like this is our mixture of ethylene glycol and water, it's an even more steep drop. Okay, it's a very, very steep drop to the point where depending on where you are, your antifreeze can work to minus 30 degrees. It goes much, much lower depending on where you are in the country. There's no reason for you, if you're in Arizona or Texas, to have a incredibly an incredibly concentrated antifreeze, because it would just cause other problems for your engine. Okay, the boiling point. The boiling point that we have here, it says a substance changes phase at boiling point. The intermolecular forces are lower in gases. So once again, we see this intermolecular attraction between hydrogens and oxygens. So if you were to look at this right here is an attraction. Okay, in order for something to go from a liquid to a gas, you have to sever these attractions. Those attractions can't be there anymore. So you need energy in order to break these intermolecular attractions. Well, whenever you add a solute, the sodium chloride interferes with that, because now the attraction here is greater, and you have to break these attractions in order to get it to move. So because the attractions are greater, the boiling point will actually elevate, and so that's what you see here. Boiling point is elevated. So that's why we add salt to water when we cook pasta. It says it speeds the process up because if you have boiling water with salt in it, instead of it being 100 degrees Celsius, it moves to, let's say, 110 degrees Celsius. And so the process of cooking the pasta is quicker. It doesn't take as long because the water is a higher temperature. So it also is done to add flavor to the pasta itself, but it also helps it cook faster. So when you look at these, there are two equations that govern this freezing point elevation or freezing point depression and boiling point elevation, and that's this delta T is equal to IKM. Now, this M stands for molarity, or excuse me, molality. Now, the reason why we use molality instead of molarity is because remember when we're doing something where the volume can change, you don't want to use molarity. Okay, whenever you look at this I term is talking about the number of ions in a particular substance. So if you were to look at sodium chloride would have two ions. There's an Na plus and there's a Cl minus. If you were to look at something like Na2O, this I factor, this Van Hoff factor, would be 3 because you'd have two Na plus ions and then you would have one O2 minus ion for a total of 3 ions. So that's what they mean by the Van Hoff factor, is how many ions there are. The Kf and the Kb are constants depending on the solute and the solvent. So is it sodium chloride? Is it going to be, what substance is it going to be? So those are constants. And then finally you have the molality, which we've already talked about. It is really important that you understand that whenever we're talking about the boiling point, that you are going to have a positive change in temperature. And then whenever you're talking about the freezing point, we're going to have a negative change in temperature. Okay, so you're going to have a positive boiling point elevation and a negative freezing point depression. So in this one it says 1 mole of each substance below is added to separate beakers containing 100 mils of water. Which will have the greatest boiling point? So if you were to look at this, we're adding 1 mole of each substance. So because of that, the molality is going to be the same. Okay, molality is the same because you have 100 mils. We're going to assume the constants are going to be the same, and now we're just going to look at it in terms of the Van Hoff factor, which is the I. If you were to look here, I have 2 ions here, I have 3 ions here, I have 4 ions here, and I have 5 ions here. So just looking solely at the Van Hoff factor, we would expect this substance right here to have the greatest boiling point elevation. Because if you were to look, delta T, B equals I, K, B, and then molality. These factors are constant, so we're not going to look at those. So that lets us just look at the I term. The one with the greatest I, which is this, is going to have the greatest boiling point elevation. Next it says 45 grams of salt is added to 6.4 liters of water at 90 degrees Celsius, where the density is this. What would you expect the boiling point of water to be? So we know this is a boiling point elevation question. So what we need to do is we need to look at the formula for boiling point elevation. And that's delta T is equal to I, K, and then molality. So if we were to look at this thing, the first thing that we need to realize is you actually need to know this K value. And it's not given to you. It should be given to you as a 0.512. The second thing we need to realize is we're talking about salt, which is NaCl. So because of that, we know that this I term is 2. So now the rest of this question is in determining the molality of this particular solution. If we can figure out the molality, we'll be able to figure out the change in temperature. So now this says 45 grams of salt. So you have 45 grams of salt, and that's per 6.4 liters of solution. So the first thing that I want to do is I want to go ahead and go from grams to moles for sodium chloride. And if you were to do this, you would say, okay, well there's 58.5 grams in 1 mole of NaCl. So now that I've done that, I'm in NaCl. Okay, once you're in NaCl, you can go ahead and say, okay, now I'm in moles per liter, which is molarity, but that's not going to help me. I need to be able to get it into molality. So what you would do is you would say 1 liter is 1,000 mils. And now you can use the density. The density would be 1 mil is 0.9653 grams. Okay, once you've done that, you can now say, okay, well there are 1,000 grams in the 1,000 grams in 1 kilogram, and that's for our particular solvent. Now we've converted, so now if you look, we went from liters to mils, mils to grams, grams to kilograms, and now I'm in moles per kilogram, which is exactly what I need for molality. If you were to take this and multiply it out, you get a number of about 0.125. So that right there is the molality of this particular substance. So we have the Van Hoff factor, the constant, the molality. So you take 2 times 0.512 times 0.125, and you get a very, very small boiling point elevation of about 0.128, which means that the boiling point of this solution would be about 100, 0.128. Next, it says many different areas of the country have different mixtures of antifreeze for use in their cars. Determine the appropriate ethylene glycol levels for the 5 geographically distinct states. So the first thing that you want to realize is this is the average annual temperature. So if you were to look at this, you're looking at right here is going to have to be the point in which you have your blue regions. These dark blue regions are going to have to be represented by this 70% ethylene glycol mixture. So you'd say that's about 70%. Now these gray ones are not nearly as cold, but you're probably going to have to stick somewhere around maybe a 60%. Okay. Now once you get in here into these yellow regions, you still see freezing temperatures. It still gets very cold, but it doesn't get nearly as cold as it does in these gray and these dark or these blue temperatures. So what we're going to do is we're going to go ahead and back the percentage down, maybe around 60, maybe 50, or 50% would probably be good. So we say about 50%. In this orange region, it very, very rarely gets that cold. So you're probably going to be okay with maybe a 40% mixture. Okay, and then finally, this orange one, this dark, I guess it's red, this orangish red color would probably be okay with even maybe a 30% solution. Okay, because that if at a 30% solution, you would still be able to drive your car up to negative 18 degrees Celsius. So you can vary the ethylene glycol level depending on where you are. Now, traditionally, everywhere south is sold 50% because 50% is generally considered to be okay for cars. But if you are up north, if you are very, very far in the north or maybe in Canada, you are looking at trying to increase the ethylene glycol in your antifreeze. Okay. The solubility, the amount of solute that can be dissolved in a substance, varies depending on a couple of things. First, we need to define what these are. So you have something that's called an unsaturated solution. An unsaturated solution is where it's holding less than the maximum that it can. So you've got 1 or 2 solute particles in there. I can add more and it will dissolve, and that's considered to be an unsaturated solution. A saturated solution is considered to be at the maximum level. So I've got as much as this solution can hold. If I were to add any more solutes to it, it would go down to the bottom and it would sit there. Okay. The last one is considered to be a supersaturated solution. A supersaturated solution is considered to be above what the maximum value that it's holding is. So you have more than it can traditionally hold. Now the reason why it's holding more is because you've changed one of the conditions. So maybe you've increased the temperature or you've done something to change the characteristics of this solution so that it is considered to be above what it generally holds. This is what happens whenever you have a supersaturated solution and you put what's called a seed crystal in, or a seed, it crystallizes almost immediately. So this was a supersaturated solution. You put some sort of seed crystal in and it begins to crystallize almost immediately. These are the 3 main factors that affect the solubility of solutes in solvents. Number 1 being the temperature, number 2 being the pressure, and number 3 being the nature of the solute. So you should be able to relate all these to individual atoms. Okay, whenever you're talking about individual atoms, as you increase the temperature, these atoms move much more quickly. Okay, so they're moving faster. As you increase the pressure, molecules are being squeezed closer together. And then the nature of the solvent and solute means, is it polar, or polar nonpolar? Okay, that's kind of the relationship you're looking at there. All right. So for solid solutes, things like sugar, things like salt, things like copper sulfate, the solubility of the solid will increase as temperature increases. Now we're assuming that we're talking about a liquid solvent here. Okay, but if we're talking about a liquid solvent, as you increase the temperature of that solvent, you will allow more of these things to dissolve. And the reason why is as you increase the temperature, you give these things more energy to rotate. And as these molecules rotate, the positives and the negatives can align up more and they can dissolve more of the solute. So, as you increase the temperature, the amount of solid solute will increase. For pressure, you cannot compress a solid. Okay, so solids cannot be compressed. So if you were to take something and squeeze a solid, it makes no difference on it. Because of that, pressure has no effect on the solubility of a solid. For gas solutes, the solubility of a gas decreases as temperature increases. So it's the exact opposite of solids. So generally speaking, as you want to increase the amount of sugar, you raise the temperature. But if you want to increase the amount of gas, like we have here for carbon dioxide, you actually need to decrease the temperature. That's why whenever you drink something like a Coke or a Diet Coke that's been warm tends to be flat, because flat means that there's less gas dissolved in it. Now, one of the things that you can do to increase the amount of gas solute is you can increase the pressure. Okay, whenever you increase the pressure, it increases the solubility. And you see that every time you open a Coke. Whenever you open a Coke, it makes a sound, and whenever it makes that sound, it's because gas is escaping. The reason why is the bottle or can is stored at a higher pressure than the area around it. Okay, so it says a salt solution is used to store salt. It says the solution is confined to a fixed container. What can be done to increase the salt in the container? So the only thing that you can really do at this point is you can increase the temperature. Okay, there are no really other options. You can't increase the pressure because salt is a solid, so it won't work. So really the only thing you can do is increase the temperature. Okay, next it says predict which one of these substances is likely to be a gas. So if you were to look right here, you have temperature, and then here you have solubility. So remember, whenever you're looking at increasing temperature, you're looking primarily for decreasing solubility. So the one that has a consistent pattern of decreasing solubility is this one right here. Okay, so that makes it our most likely candidate to be a solid, or excuse me, to be a gas. Now, some people will take a look at this one right here and say, well, look, this one decreases right here. And you're right, but it also increases. So you're looking for one that consistently decreases as far as being a gas is concerned. And finally, it says, does crushing a substance such as salt increase the solubility of salt? It says justify your answer. And the answer is no. And the reason why is that was not one of the factors that increased the solubility. What it does do is it allows it to become soluble more quickly. Okay, if you can crush them up into tiny particles like this, it allows the water to arrange itself around the molecules more quickly. So you have your sodium and the water molecules can come around it much more quickly. Okay, so that is, in terms of speed, yes, but in terms of absolute solubility, the answer is no.